So in this video, what we're going to do is use our fundamental identities, our ratio, reciprocal, symmetry, Pythagorean identities to verify other identities. So here we are given an example where we have a product of two trig functions equaling the cosine function, and we're asked to verify that this is an identity. And as we mentioned before, what this means is that this side should be the same as this side for every value of x. There shouldn't be just specific values of x for which the two sides are equal if they are identities. Another way to think about it is if we were to graph the left side and graph the right side, if they are truly identities, the two graphs would match up exactly and we would not be able to see any difference between the two graphs. When you try to verify an identity, when you try to establish that two trigonometric statements are equivalent using other fundamental identities, the way that you do it is you start with the more complicated looking of the two sides. So in this case, I would argue that this side looks more complicated than this, and you take and rewrite the side that looks the most complicated. So we're going to start off with a really simple example. And then what you need to do is use those fundamental identities that we discussed in previous videos to manipulate or rewrite the left side into equivalent statements until we reach a point where we have this statement on the right hand side. So again, pick one of the two sides, usually the more complicated one, write it down. Do not write down the original statement. When we get done, we want this statement. So I'm going to rewrite the cotangent function using the reciprocal identity that the cotangent of x is equal to the cosine of x over the sine of x. So that's using a reciprocal identity. And then what we want to recognize is that this can be rewritten as sine x over sine x times the cosine of x. Using the commutative properties of multiplication, we can separate them differently than how they're initially separated. And clearly sine x over sine x is 1, as long as the sine isn't 0. And we get 1 times the cosine of x. And 1 times the cosine of x is just cosine of x. So what I wind up with is a verification of the identity that I was given. I have demonstrated that the left-hand side can be manipulated to produce the right-hand side of the identity. So here's another example. So again, look at the two sides and select the one that looks to be the more complicated. I'm going to argue that the left-hand side looks more complicated than the right-hand side. I'm going to rewrite the left-hand side of the identity, or the thing I'm trying to prove is an identity. And then what I'm going to do next is use the distributive property to distribute the tangent into the function, or into the parentheses, sorry. So I'm going to get tangent of x times cotangent of x plus tangent times tangent is tangent squared of x. And there's something I could recognize here. If I recognize that the tangent and the cotangent are reciprocal functions, then this product tangent times cotangent just equals 1. In other words, if the tangent of x is defined to be y over x and the cotangent is its reciprocal, then y over x times x over y, as long as x and y aren't 0, this product is going to equal 1. So in general, the product of reciprocals equals 1. If I don't recognize that offhand, I can use the reciprocal identity to rewrite the cotangent function as 1 over the tangent function. And this would be plus the tangent squared of x. And tangent times 1 over tangent is just tangent of x over tangent of x plus tangent squared of x. And tan x over tan x, as long as tangent isn't 0, then this ratio is 1, so we get 1 plus the tangent squared of x. And now I have the sum of two squares, which tells me I should investigate the Pythagorean identity. And my suggestion before was that you memorize cosine squared plus sine squared at a minimum, because you can always manipulate this to get the other Pythagorean identities. I see a tangent squared right here. So I know to get a tangent squared I would need to divide the sine squared by cosine squared. So I'm going to go ahead and divide both sides by cosine squared to produce a tangent squared. So when we do that, we get cosine squared over cosine squared is 1 plus the tangent squared of x equals 1 over cosine squared is secant squared of x. And that tells me that 1 plus the tangent squared of x by a Pythagorean identity can be replaced with the secant squared of x. And at that point I've verified the identity because I've been able to manipulate the left-hand side into the right-hand side using a series of identities. So we'll look at another example. So I'm going to argue that the left-hand side again looks to be the more complicated side. So start by rewriting the left-hand side. So tangent squared of x. The key with identities is to recognize that there isn't going to be a right way to do it. There's usually going to be many ways many routes you can take to manipulate things. So I'm showing some examples. I'll actually do this one two different ways. So one approach would be to recognize that the tangent squared shows up in both terms and can be factored out. So I could use the distributive property to factor out a tangent squared, which would leave behind a cosecant squared. And factoring a tangent squared from here would leave a minus 1. And now I see a difference of two squares sitting here, which makes me think that there's a Pythagorean identity looking at me. So I remember that cosine squared plus sine squared equals 1. Until you memorize all three, you can always manipulate this basic Pythagorean identity to get the others. I see a cosecant squared, and I know that cosecant is 1 over the sine squared. So to generate a cosecant squared, I divide both sides of the Pythagorean identity by sine squared. Divide by sine squared of x. And cosine squared over sine squared is cotangent squared, plus sine squared over sine squared is 1 as long as sine isn't 0. And 1 over the sine squared is the cosecant squared. And I see that if I subtract this 1 from both sides, I get that the cotangent squared is equal to the cosecant squared of x minus 1. So I can replace the cosecant squared minus 1 with the cotangent. So we'll do that we'll do a substitution, replacing this Pythagorean identity with the cotangent squared. And now I can either recognize I have the product of reciprocals, which equals 1, or I can continue to manipulate. I know that the cotangent is 1 over tangent, so cotangent squared is 1 over tangent squared, which gives me tangent squared of x over tangent squared of x, which just equals 1 as long as the tangent function isn't 0. So I could have taken a different approach to the same identity, and this is just to drive home the idea that there isn't a right way to do these. Again, start by writing the more difficult looking side. Just transcribe it. Tangent squared of x times cosecant squared of x minus tangent squared of x equals, and then let's rewrite these two. Tangent squared is equal to sine squared of x over cosine squared of x times cosecant squared of x is the same as 1 over the sine squared of x minus the tangent squared of x. And I can see from here that a sine squared over sine squared is going to be 1, so it's going to leave me with a 1 over the cosine squared of x minus the tangent squared of x, because this divided by this equals 1 as long as the sign isn't 0. And 1 over the cosine squared is a reciprocal identity. This is the same as the secant squared. The secant and cosine functions are reciprocals of each other. And now I have a difference of two squares, which tells me I should be looking at the Pythagorean identity. Cosine squared plus sine squared equals 1. And to generate a secant, I would need to do 1 over the cosine squared. So I'm going to divide both sides by the cosine squared and see what that looks like. And 1 over the cosine squared is just the secant squared of x. And here I get 1 plus sine squared over cosine squared is tangent squared. And then if we subtract the tangent squared from both sides, we get 1 is equal to the secant squared of x minus the tangent squared of x. So I can replace secant squared minus tangent squared with a 1, and I verified the identity by manipulating the left side using identities until I get the right hand side to pop out. So we'll do one more example before we do things that have ratios. So here I have cotangent of x times cosine of x equals cosecant of x minus sine of x. And this is one where you look at it and it's kind of hard to make an argument for which of the two sides are or is more complicated looking. I'm going to run with the right hand side. So I'm going to start by transcribing it. Cosecant squared minus sine of x is equal to, and I know that the cosecant is just 1 over the sine, and this is minus the sine of x. And I have a product here, so I need a way to get these two separate pieces as a single piece. And I'm going to argue that finding a common denominator is going to be one way to kind of bring those two pieces together. So we want to take and investigate this. This is going to equal 1 minus the sine squared in the numerator over a denominator of the sine of x. We've got the common denominator. This looks like the Pythagorean identity. We have cosine squared of x plus sine squared of x equals 1. So if we subtract the sine squared from both sides, we'll get 1 minus the sine squared of x, which is exactly what we have in the numerator here. So we see that can be replaced with, the numerator can be replaced with the cosine squared of x, still all over the sine of x. And I need a product of two functions. So I want to break this up so it looks more like a product. I'm going to break it up with a cosine of x over the denominator sine x times, this was cosine squared, so I need to be times a second cosine function. And cosine over sine is the definition of the cotangent. And this is cotangent times cosine, which is what I had on the left-hand side. So I have verified the identity.